Good evening, everyone present here.
At high pressure,
Respected principal, sir, honorable distinguished guests, all the respected faculty members, and my dear students. I, Porinita Borwa, on behalf of the Department of Chemistry, Jorhat Kendra Mahavidyalaya, welcome all of you to the online session for IIC calendar activities. A popular talk titled Commercialization of Lab Technologies and Tech Transfer is organized by the department in association with IIC and IQAC of Jorhat Kendriya Mahavidyalaya.
Okay, very good. So, as you all know that as in CSR Institute, we have a mandate that we have to do basic research, which will be related to translational research only. So this is the mandate of CSR institutes. There are 38 laboratories all over the India under Council of Scientific and Industrial Research. This is a autonomous council, and the Honorable Prime Minister of India is the chairman of this council, and Honorable Minister of Science and Technology, he is the vice chairman of the council. So only one such type of laboratory is here in Northeast India, that is CSIR Northeast Institute of Science and Technology. So our mandate is to utilize Northeast resources, utilization of Northeast resources for the betterment of society as well as science. So with this mandate, actually, we are very much related to develop technology, and without doing basic research, it is not possible to do technological work. That's why the title is very relevant for me. And in this lecture, I will try to cover some general things, and the later stage I will try to cover our technological work, and to achieve these technological works what we have done, uh, basic I will cover for the benefit of the students, mainly for students. Also, I think it will benefit for to the faculty members also, because now in the government of India's mandate is indigenous technology development. So yesterday it was National Science Day. So this Science Day theme was the indigenous technology for Viksit Bharat. So it is very relevant for today's lecture also. So the topic, as you know, that this was decided by your authority only. So process for innovation, development and technology, readiness and commercialization of lab technologies and tech transfer. So it is very good topic, and we can cover a lot of things here. So I will also try to cover all those things. And I have made my presentations in such a way that everybody can understand this. So first of all, I want to say about the indigenous technology challenges, because you see, we are now thinking about Viksit Bharat. We are now thinking about our indigenous technology. We have a lot of resources. Only thing is that we have to validate those things, and we have to take them from lab to land. So what is indigenous technology? It refers the innovations and advancements that are developed within the country's borders using local knowledge, resources, and expertise. This is actually indigenous technology. Historically, there are strong connection between indigenous knowledge, science, and innovations. So, what is indigenous knowledge? That may be climate regime and geomorphology, cultural context, experience of particular type of disaster, socioeconomic context, or globalization. These are called indigenous knowledge. So, why indigenous knowledge is important for modern world? You see, indigenous knowledge means indigenous technologies. It can empower a nation to innovate, adopt, and thrive. They are the cornerstone of self-reliance and national development. So, why it is important to develop any technology from our indigenous knowledge? Because we are learning from indigenous knowledge, protecting the endangered way of life, approaches to the natural world, approaches to health, lifestyles, and diet, views on equality in the community, view on materialism, and to realize the different ways of viewing the world and gathering knowledge about it. That's why indigenous knowledge is very important for modern world. We can't skip this indigenous knowledge. So some indigenous technology we have developed which are very much successful. I think you know about Aryabhatta satellite. I think you know about Green Revolution. You know about Pokhran test. So these are technology developed by indigenously from our indigenous knowledge. You see, Green Revolution, for this Green Revolution, and this time MS Swaminathan, he got Bharat Ratna Award. So another success story is Chandrayaan 3 mission. And this is the theme of Chandrayaan 3 mission. These are indigenous technology only. So I will cover
Madam, Madam, sorry to interrupt, but the slide is not moving, your slide.
Oh, is it?
Yeah.
Okay.
Change your side.
Is it okay now?
Okay. I would like. Yes.
Now?
Chandrayaan 3, now Aditya L1.
Yes.
It is now moving.
Okay. So next success story is Aditya L1, India's solar mission. And in the healthcare sector, you can see the robotic surgery. You can see a lot of things in medical technologies, in telemedicine, and indigenous drug discoveries also. These are all indigenous technology. And in the for global COVID-19 pandemic, what was India's contribution? We all know. Is the government of India launched the largest vaccination drive across the country, and India manufactures more than 60% of all vaccines sold across the globe. First success story is Covaxin, then Covishield, and then Sputnik V. You all know. So these are indigenous technology, and besides this, India has developed 4 indigenous vaccines in just 2 years. The 4 vaccines are ZY-CoV-D, world's first, and India's indigenously developed DNA vaccine. Then Corbevax TM, India's first protein subunit vaccine. Then Zemcovac 19, in world's first and India's indigenously developed mRNA vaccine. Then IIC CC, world's first and India's indigenously developed intracellular COVID-19 vaccines, and many more. Those are India's indigenously developed vaccines. So that's why Indian government has focused on indigenous technology, and you can see the current technological landscape also in the agriculture field. This precision farming, you must know these things, organic farming and crop specific technologies. These are in these areas actually India has developed a lot of technologies. And recently, CSR has also launched the technology. That CSR has developed the technology and also implemented also in the field of Jammu and Kashmir. That is lavender cultivation, high yielding lavender. Also, lavender has a lot of demand. You see, lavender oil which sells for at least rupees 10,000 per liter, 10,000 per liter, and 100-acre land. CSR has cultivated lavender, started lavender cultivation. That's why it is called as purple revolution. The lavender and the demand of lavender is very high in country as well as globally. Its demand is very high. That's why already we have started in purple revolution indigenously developed with indigenously developed technology in India. So another thing is documentation, digitalization and scientific validation of traditional knowledge. We should not ignore the traditional knowledge. Actually, you see, if you can think that how it will go from lab to land. So for transferring a technology from lab to land, so in this traditional knowledge can work, and those traditional work, those traditional knowledge which our grandmothers, those things, traditional knowledge we can use, and we have to, but before scientific validation we have to make documentation, and we have to digitalize all that knowledge, and most importantly we have to validate those traditional knowledge scientifically. Then after the in the validation stage, that can be validated in the lab itself, and if it will be validated, then those things, scientific validated things, we can forward it to the land. This is the concept about the traditional knowledge, how we can transfer the traditional knowledge from lab to land. So this in the Vedic period, you see this whatever knowledge they have, or some of our rural people have, so those things we can scientifically validate, and we can transfer those knowledge from lab to land in terms of technology transfer. So as I have been working in the area of membrane science and technology. So in this area, actually, already the concept has been established in foreign countries, but concept has been established in India also, but industry not yet started in India. But industry, lot of industries have been started in foreign countries, that those are related to membrane science and technology. Membrane technology actually very much successful in some areas like cleaning for water treatment or water or wastewater treatment. So this this membrane science is very much effective for removal of heavy metals, removal of organics, removal of biological contaminants, etc., etc. So using this technology, we have been working for the society through development of membrane device for getting the cleaning water for the society or for the industry. Actually, as students are there, so I'm just showing these slides how membrane technology will come to the picture. You see, I think if science students science students are there, then you know about the semi-permeable membrane. Actually, membranes are developed. Membranes concept has it was established in 1748. That period is progress in membrane science, and Y. Jacob from France in 1949, he has established the concept related to thermodynamics. Actually, membrane is nothing but it is a thermodynamical concept that is basically depends on thermodynamics, that transport phenomena that is depends on thermodynamics. But from then onwards, people are working on membrane science and technology. But in 2003, one of the initiator of membrane science, that is called, he's known as Professor Enrico Drioli. He's from Italy, and he made an opinion that in the earlier membranologists were very optimistic about the possibilities of membrane, but the results achieved today are sometimes beyond their expectation. So this is the actually turning point of membrane science area, because whatever researcher has achieved the results, those are very beyond their expectations. That's why now membrane science is a very very good area to work, good research area to work, and its application is in lot of areas like automobile industries. They are using this application of membranes in their work, and drug and pharmaceutical industries, chemical, metallurgy, food industry, everywhere membrane technology is applicable. You see catalyst support on, and most well-known example is drinking water treatment. You know the reverse osmosis system. You know our some aquaguard. I think all of you use aquaguard. Those things are already in the market. So in case of wastewater treatment also, this technology is applicable. Foreign country has applied. And pollution prevention also. For pollution prevention, we can make membranes for separating some harmful gases. Indoor purification, fine chemical industry, petroleum industry, everywhere membrane can be used. So I am telling membrane, and membrane, but what is the definition of membrane? You see, membrane is nothing but a selective barrier that may be solid or may not be solid. It separates the components. If you have a mixture of 3-4 components, then membrane can separate the components. Membrane can work by driving forces like concentration, electrical potential, or temperature. Sometimes membrane will work depending on the concentration, sometimes electrical potential, and sometimes temperature. And this driving force, concentration, electrical potential, or temperature, anything, these three are the driving forces. Anyone can work, but this driving force only make the mass transfer possible. That is, whatever membrane will work, that is due to the whatever membrane will separate, those things will be separated for the mass transfer, only. So earlier concept was to make membranes using polymers only, which are commercially available polymers. Now people are working on hybrid membranes, very high purity or very updated product, and those are polymer composite. So what we are doing in our laboratory, we are making some hybrid nanocomposite with advanced properties. So hybrid nanocomposite we have prepared, and those hybrid nanocomposites we have applied for designing of membranes. So how membrane can work? You see, membrane can work depending on some mechanism. Those mechanisms, actually, in membrane some pore sizes are there. Depending on the membranes are categorized as microfiltration, ultrafiltration, nanofiltration, or reverse osmosis. So these membranes will work depending on some principle. That is, first one is size exclusion. Size exclusion will work if the membrane pores, in the membrane some pores are there. Those pores we can determine by characterizing them with some these sophisticated instruments like scanning electron micrograph, transmission electron micrograph, or atomic force micrograph, AFM. Like that, we can we can characterize the membranes, and we can determine the pore sizes, whether it is in the nanofiltration range, microfiltration range, or ultrafiltration range. So those membranes will work according to the principle of size exclusion. It means if a bigger molecule is there, and if a mixer contains a bigger size molecule and a smaller size molecule, then if you can separate those molecules, then the separation is possible due to the membrane pores. And if you give if you treat the membrane with the solution, that solution mixture of bigger and smaller molecule, then smaller molecule can be permeated through the membrane and bigger molecule can be rejected by the membrane. That is the size exclusion principle. And sometimes electrostatic interaction is there. If you are chemistry student, then you know about the hydrogen bonding interaction. So those electrostatic interaction is there in some cases. In some cases, charge repulsion. Suppose positive charge is there in the membrane itself, then positive charge molecule, that due to repulsion, that the membrane can reject some molecules. And solution diffusion also, sometimes diffusion will occur, and sometimes hydrogen bonding interaction. Those are the different mechanisms involved during the membrane separation processes. So what are our work? I am going to give you the work whatever we have been doing in our laboratory. Later on, I will give the example how we can develop technology using these membranes. That's why I am giving here some I'm showing here some of our work. This type of work, we can forward this type of work from lab to land also. Those things, what these membranes, how we can take it from lab to land, that there also we have to do lot of work after doing basic work. So those things also I will cover, because our title is like that. So in our laboratory, what are the hello okay, what are the work we have done? As I told you that we have done membrane, we have done work for transforming membrane technology with advanced polymer nanocomposite. So we have done some work for removal of dyes from wastewater, separation of biomolecules, mixer gas separation of olefin, paraffin, some industrial gases, and we have developed some biodegradable packaging material, membrane-based sensor we have developed, removal of heavy metals from water, they say arsenic, chromium, copper, like that we have developed, and biomedical application, suppose wound healing application, we have developed our membrane, and treatment of petroleum industry wastewater, those things we have been working, and photocatalytic degradation of pesticides, those are also in this area also we are contributing, and separation of enantiomers, those things also we have been continuing, and from lab to land concept, actually we have done some work for biomolecule separation. Those work I will cover in my lecture for lab to land concept. So for developing the membranes, we are using this type of material, polymers, cyclodextrin, calyxarin, dendrimers. I think some of these compounds are new for you. Some may know. Dendrimers, carbon nanotubes, I think you heard about it, and graphene oxide, reduced graphene oxide, mesoporous and microporous materials, cellulosic materials, etc. So before development, we have to do lot of basic work, various steps for development of technology related to membranes are selection of polymer, development of functionalized materials, characterization of functionalized materials, selection of solvent for dissolution of polymers, nanocomposite, design of membrane, characterization of membrane, design of membrane module, development of experimental prototype, application of membrane, and simulation and modeling. This is actually a multidisciplinary area, so we have to do lot of multidisciplinary work for developing a membrane-based technology. So these are the different steps for designing a membrane. First of all, you have to solubilize the polymer composite or polymer nanocomposite. Then casting we have to do. Then after casting, evaporation of the solvent we have to do. Then coagulation, we can use coagulation bath for phase separation. Then we will get the solid membrane. Then this solid membrane we have to characterize using different instrumental techniques for determination of pore size, morphology, thermal properties, up to which temperature the membrane will work, zeta potential, that is whether membrane surface is charged, a positive charge or negative charge, contact and angle. This will determine the hydrophilicity or hydrophobicity of the membrane, whether membrane is water lover or water hater, that we can determine from contact angle measurement, then water permeability, etc. So our approach towards membrane science, as I told you, that these are our approach, and we have developed membranes for our technological use, and these are the after developing the bench scale work for membrane design, we can make the membrane big sheet of membranes using this type of equipment. So we can get membranes up to 14 feet long and 1 feet breadth. This is the one type of membrane, and this membrane we have prepared here, which is transferred to USA based company, and this is membrane module for use in industry. And this is one compound which we have purified or separated using this type of membrane. We have another membrane preparing machine. This is called hollow fiber membrane making machine. So these are the fibers. We can prepare this type of fiber up to 500 meter long in a single run, and these fibers we have put here in this type of casing, which is called membrane module. These are designed by us after doing lot of engineering works, modeling and simulation works, etc., etc. And this is another technology we have developed at CSIR NIST using our membrane technology. So actually these are technological work, but before doing this, we have to establish the procedure in bench scale. So before in that period, when we have been working for developing a technology, we have to do a lot of basic work, as I told you earlier. So this type of basic work will give us some very good publications like this. You see, this is gas separation work, or gas separation, carbon dioxide, nitrogen separation. This is published in a very prestigious journal that is called Chemical Communication. And this is another work we have published in another prestigious journal. This journal's impact factor is very high. This is on biomolecule separation. This is separation of epigallocatechin gallate, which is a T catechin, very important, industrially important, and T catechin has a lot of medicinal value, antioxidant, anti-cancerous, etc. So for wastewater treatment, we have developed some membrane. We have designed and developed some membranes, which the work has been published in very high impact factor journals. So this is also here we have used quantum dot beta cyclodextrin nanofiller for developing some membranes. These all are developed in bench scale. So bench scale work we have published in high reputed journal. These are also or some works we have published recently. These works are very recently we have published in very reputed journal. So this is one example of developing a membrane which is useful for pharmaceutical sector. Actually, you may know that if we will take one medicine, one tablet, then that tablet has some adverse effect. As you know, the ibuprofen. This is the paper we have published on Journal of Membrane Science, very high impact factor journal. So this work we have done for ibuprofen. You see, ibuprofen is mainly used as painkiller. So you all know that painkiller has some side effect. Why it has some side effect? Because ibuprofen contains two isomer. Only one isomer has a medicinal value, but another isomer has some adverse effect in human beings. So that's why the side effect is there if somebody use ibuprofen. So what is the what we have done here, we have separated the isomers. Ibuprofen has S isomer or R isomer. So we have separated both the isomers and we get the S ibuprofen separately, which has only the medicinal effect. Using this type of membrane, we can separate the isomers, ibuprofen isomers, which can change the pharmaceutical change the life of pharmaceutical industry actually, which can save the life of human beings from the side effect of medicine. This type of membranes we have developed, and you know the adverse effect of synthetic food packaging material. So we have developed smart food packaging material which is biodegradable, as well as it will give the indication of spoilage of food. This is also, we have developed some thin film for packaging as packaging material. This type of bag we have prepared using some natural resources. Here actually we have used some grass, available grass. So from there we have developed some colored material. This colored material, if you put some meat and fish, then this color material, if the food meat and fish will be spoiled, then the color of the bag will vanish. Actually, this is like a sensor for determination of spoilage of meat and fish. This is also we have published in very good journal. And biomedical application also, we have developed some antimicrobial fabric which can protect the human from the effect of antimicrobial bacteria or like this. So antimicrobial fabric we have developed, which can be used as mask or other things. These are the recently developed work, and you see how these things we can take forward from lab to land. So I'll give just some example how we have done this type of work. So you see here in this work, I have shown in my earlier slide, like here you see, here we have developed these membranes for separation of or purification of this compound. Suppose oxyresveratrol, this is very good compound available in some plants here in Northeast India. So which compound can be a very good medicine for Alzheimer patient actually. So this type of work we have developed in bench scale, and this work for production of this type of compound oxyresveratrol, we have developed the technology after doing lot of work. So if you consider that how we can take this one technology from lab to land, after completion of basic work we have to do lot of pilot plant work. It is in a large scale. So suppose my objective is development of membrane-based technology for commercial production of oxyresveratrol and natural dyes from plant species. Suppose I have to develop some technology which can be forwarded from lab to land. So from lab to land, how it will go, these steps are here. You see, after I have shown you all the basic work, after finishing this, after completion of this basic work, we have to do some scaling up work. Those scaling up work, suppose I have considered a material which we can get we can get from plant species. Suppose most easy technology. Suppose we have to extract something from plant source. Then what will be the steps we have to do for developing the technology for getting the pure compounds? You see, I will consider only oxidized bilateral. So first of all, first step will be the resource. So determination of resources, findings. Actually, we have to find where we have to get this specific compound. So plant, I am considering here only plant, plant-based molecule. We for obtaining plant-based molecule, we have to develop the technology. Suppose so. First of all, we have to search the plant, in which plant that particular compound is available. This is literature data we can get, and some literature data, and suppose some we can get some informations from traditional knowledge also. Then next step is extraction, how we can extract that compound from the plant itself. Then after extraction, design of membrane will come for purification of compound. So evaluation of membrane performance, this we can do in the basic research itself. Then we have to design the flow chart. Then cost analysis we have to do. So first of all, for considering any technology, we have to do some work. What is the uses of that compound? That we have to do. If the compound has industrial importance, then only you have to go for the technology. Otherwise, the technology, it will not have any industrial feasibility. That's why uses of that compound, what is the demand in industry of that compound, that is you have to check in the preliminary stage itself. So suppose compound, as I told you, that plant, we will consider plant we have to take. Then we have to do some we have to reduce the pieces of the plants, then mill to lab. At mill we have to make small pieces. Then from the mill, these pieces from mill to lab. Then chipping we have to do. These are the different stages. And drying, we have to know what is the moisture content in that raw material. So after that, we have to fabricate the extraction unit. You mind it, these things you have to establish in the bench scale. After establishing in the bench scale, we have to do pilot scale work using a large setup in pilot scale. So this is suppose extraction unit. Then this is the drawing we have to make, the extraction unit drawing. This is after doing lot of engineering calculations. Then fabrication and installation of membrane module. As I told, these are the basic data, basic characterization data, as I told earlier. Before doing pilot scale work, we have to characterize all those things for suppose membrane or other materials. Then membrane module and large scale preparation. You see, large scale preparation of membrane for one of our technology. And this is the membrane module we have made here. This is the pilot scale setup. After establishing our work in the bench scale, this is the pilot scale setup, and this is the pilot scale work is going bench scale. This is the bench scale setup, and this is depending on the success story of this bench scale setup, we have designed this pilot scale setup. So this is the case actually. If you take the technology from lab to land, this is lab concept and this is land concept, you see. So this is the 3D drawing for this technology, for this particular technology, we have to prepare all those things to show in the industry. So this is the design of whole plant for the technology. And after developing all those things, we have to optimize the process parameters, how the industry will do this work. We have to give all the conditions to the industry for establishing it in the land. So these are also purification also in the pilot scale work. These things we have done, and then ultimate product, the characterization work we have to do. This characterization work, lot of instruments are there for to characterize these all things. And this is for our technology. We have characterized our end product using HPLC, and that a product has purity is 99.8%. You see, this product purity is 99.8%. This is confirmed by GCMS analysis. This is the single GCMS peak after doing this pilot scale work. So this is the flow chart. For lab to land concept, we have to design the flow chart also. This is the flow chart for whole technology. And for giving this technology, for transferring this technology, we have to do cost benefit analysis also, because we have to give what will be the gross profit after establishing this industry. So we have to do lot of calculations. Then break-even analysis. You see, this is the break-even point, gross profit. If somebody will establish this industry for production of particular for specific compound, then that gross profit will be 1.3 crore per annum. These things we have to calculate, and we have calculated here. You see, project capital cost for establishing this type of plant. What will be the project capital cost per annum? 91.8 lakhs, and total cost of production per annum is 74.98 lakhs. These calculations we have to do for transferring any technology. So this is the gross profit. But you see, investing this much money, the person, if somebody will establish this technology, his profit will be 1.3 crore per annum. So this is the actually lab to land concept. So this type of technology we have already transferred. This technology we have transferred, and this technology also we have transferred to NRL. Doing this type of things, and this is my lab facility. This is my lab facility. We have good facilities for this type of research, and some renowned personalities, they have all visited our laboratory during COVID also, after COVID also, before COVID also. So and with NRL also, we have signed MOU for 90 crore agreement for 90 crore project. That is actually we have established our work in some industries. That's why they are very much confident on us. So they have given us some project, and this project actually we have signed MOU very recently on 27th December 2023, and this is a 90 crore project. And this is our group, another success story. This is, I have shown you one gas separation work published in ChemCom. That paper is very much cited in 2023. I think in 2023 November it has been published, but this paper has got lot of citation, and this journal for 60th birth anniversary of this journal, they have published a special issue of their highest cited papers. And this this issue, in this issue, our one article is included here. My name is here. So our NIST also tweeted this news this is a very recent success for my group. So at last, I acknowledge everybody for listening me, and also Royal Society of Chemistry, Chemical Research Society of India for giving me CRSI bronze medal. And this is my group, research group. This 8 I have already produced PhDs, and these are my research fellows. Some technical persons are also there. I have more than 10 research fellows and some technical persons. So these are all engaged in different position, ONGC or colleges, universities, in NIST itself. So they are engaged now, permanently engaged, some of them. And at last, thank you all for listening me. And that's all my presentation. Okay.
Thank you very much, ma'am, for such nice presentation. And
I have prepared very hurriedly. I have prepared actually.
still, it's very enjoying and enjoyable and
Thank you.
nice presentation, and it's very thought-provoking, enlightening, and also as well as informative for all the, not only for the students but all the present participants present
I
in
have
the
tried
session.
my best to give just a concept how we can develop a technology in bench scale, and how we can take the technology from bench to industry, bench scale to
Yeah.
industry scale. That's all actually. Just I think everybody has got some, at least smell that this type of work has to do to develop a technology, or for lab to lab concept. That's all.
Okay, ma'am. Very nice. Thank you very much. I think all the students have been benefited by her such an informative and thought-provoking presentation. Hope she mentioned in her deliberation about all the technologies, indigenous technologies, how it can be transferred from lab to land, from our forefathers' generation, how it is going from lab to land. She mentioned about elaborately mentioned about membrane technology, which is her field of research, and she showed from basic research how it can be converted to it can be transferred from bench scale to pilot project through various processes, preparing membrane. And all the students, I think all of you know about the membrane in our chemistry, in basic chemistry, all about know about osmosis, and you got this membrane, semi-permeable membrane. All these things, it is in high standard. So I think all of you enjoy it, and not only the students but all the participants present may be enjoyed by her such wonderful presentation. Thank you very much, ma'am. Besides your despite schedule, you have joined us and spend your time.
Thank you, madam.
Thank you.
Thank you.
Now it's
Actually,
time
my
to...
throat is not well. That's why
Yeah.
in between.
Okay, ma'am.
Coffee is
I understand.
yeah.
Now it's time to propose the vote of thanks. I would like to request Ms. Prayasi Datta from second semester to deliver her vote of thanks. Prayasi, are you there?
Yes, ma'am.
Okay.
Thank you, ma'am.
You carry on. You carry on.
Good evening. As we reach the ending of the session of this online meeting organized by the Department of Chemistry, I, Prayasi Datta of second semester, on behalf of my department, would like to extend my heartfelt gratitude to everyone present here. It has been an enriching experience to have all of you participate in this meeting and contribute your valuable insights. Now, first and foremost, I would like to express our sincerest appreciation to our principal, Dr. Tulen Saikia sir, for his continuous support and encouragement throughout the meeting. We are immensely grateful to our distinguished speaker, Dr. Swapnali Hazarika ma'am, for sparing us her precious time and sharing her valuable insights and expertise with us. Thank you for educating and enlightening us about this important topic. Your inspiring words have undoubtedly left a lasting impact on all of us. I also want to express our gratitude to all the faculty members present with us and the organizing committee who ensured the smooth execution of this event. Last but not the least, I would like to thank each and every attendee for their active participation and valuable contributions. Your presence have truly enriched the discussions and made this event a resounding success. Thank you once again for being a part of this wonderful gathering. We look forward to seeing you again in the future events. Hope you enjoy your evening forward. Thank you and good night.
Can we have a group photograph screenshot?
Hello, Binud. Screenshot লৈছা? Binud, screenshot লোৱা।
মই আহিছো দেই।
আহা পিনাকে আহা সকলোখিনি
তেতিয়া ভাল লাগিব।
ভিডিঅ'টো অন কৰক সকলোৱে।
জ্যোতিশিখা বাইদেউ আছে নে?
জ্যোতিশিখা
বিনুত লুকাই আছিলা।
Behind the screen.
জ্যোতিশিখা আছানে? জ্যোতিশিখা মেম
সবে ক্যামেৰাটো অন কৰি দিলে হৈ যাব।
সবে ক্যামেৰাটো অন কৰি দিয়া ভিডিঅ'টো।
সবে ক্যামেৰাটো অন কৰি দিয়া।
Students যিখিনি আছা।
See, অনিমেষ
One screenshot only.
হৈছেনে?
They are leaving.
হৈছে যেন লাগিছে মেম।
ঠিক আছে, থ্যাংক ইউ, ভাল লাগিল দেই, বহুত
ভাল লাগে।
Oh, thank you. আহিবা কেতিয়াবা, আহিব আপোনালোক।